So wind power has been with us for a very, very long time, from grain mills in the 9th century to draining and making habitable the Netherlands in the 15th century. The wind turbine that won the West, more than 6 million of these were deployed, pumping groundwater and providing irrigation during the westward expansion of the United States. The first wind turbine, electric generating wind turbine, and then finally in 1956, the forerunner to all the wind turbines that we know today. So if we look a little bit, jump forward in time just a little bit, in Altamont Pass, you can still see thousands of these deployed. Those went in the mid-'80s. These are 100 kilowatt machines. And the trend as we go with time is the turbines have gotten bigger, both in rotor diameter and in capacity. So nowadays we have multi-megawatt machines, and we look at the prototypes that are going out offshores. They're extremely large, up to 5 to 6 megawatts in size. So very quickly, what do wind turbines look like today? Well, very much like this, something you're probably familiar with. 1 to 3 megawatts in size, that's the rated capacity, which means that when it's running full bore, it's producing 1 to 3 megawatts. They operate in wind speeds of 3 to 25 meters per second. They reach rated power at about 11 to 12 meters per second. The rotor are lift-driven like airplanes, not drag-driven like water wheels. Typically 3 blades, upwind so that the rotor doesn't have to be in the wake of the tower. Full blade pitch, which means that the entire blade twists about so that it can optimally catch the wind, or in extreme wind conditions, feather. The rotor diameters are typically 70 to 120 meters in diameter, so maybe you can imagine if there was a football field overlaid with that rotor. And they operate at about 5 to 20 RPM. Typically made of fiberglass, some carbon fiber used. Carbon fiber is expensive, so that's used sparingly. It's active yaw so that the nacelle can turn and point itself into the wind. Steel tubular tower. Typically these are installed in plants for farms of 100 to 200 megawatts in size. Those in turn are often clustered together in wind resource areas because there's an excellent wind resource in that area. Most wind turbines have a capacity factor of about 40%. So capacity factor is a metric is the ratio of how much energy the turbine produces versus how much it could produce if it was running full bore. So what that means for a 1.5 megawatt turbine like this one right over here, that it produces about 5 million kilowatt hours of energy per year. Just as a basis of comparison, if you looked at your PG&E bill, you probably use somewhere in the neighborhood of about 6,000 kilowatt hours per year. Just to give a little bit more perspective, so here we are walking down between 2 blades of a 2 megawatt turbine. This can be found in Solano County, just to the west of Rio Vista. So one blade, about 50 yards in length. So this is a MM92 2 megawatt turbine. The rotor diameter is about 92 meters. The blade length is about 50 yards, and the weight of that is about 9 tons. So I want you to remember that number because we're going to revisit that in just a little bit. If we were to take a peek inside of the turbine, so we have our rotor over here. Shaft brings torque in to a gearbox that speeds things up so that it drives a generator at 1200 or 1800 RPM. The generator in turn is hooked to a whole battery of power electronics over here, which conditions the electricity. And the electricity flowing out of there goes through a set of transformers to minimize voltage losses. So how much do these things cost? Well, if I had plotted this way back here into the 1980s, it would be somewhere up around there, around the ceiling. But nowadays, the prices are, if we look at 2012, at about $1 million a megawatt. I hear more than that. Installed, the cost is about $1.6 million a megawatt. So is that a lot of money? We can take a look at wind energy prices. That's what these dots are over here, going from 2003 to 2011, and compare that to bulk electricity costs, average wholesale electricity costs across the country. And we can see that for quite a while, wind power has been very, very competitive with other sources of electric generation. Over the last few years, we see that it's creeping on the bubble and then actually a slight excursion outside of it. That, of course, is driven a lot by plummeting prices for natural gas. Not very much can be competitive with natural gas right now. Natural gas cannot be very competitive with natural gas right now. So looking at the installed capacity globally, we can see both globally and in the United States, it's gone up. Primarily driven by the increasing cost effectiveness of wind, and in some cases also favorable policies, legislations. if we take a quick peek at the country-by-country breakdown, we can see that China is ahead of the pack, although not too long ago they really didn't have any at all, and that the installed capacity in the US is very high, around 50 gigawatts, and about 240 gigawatts globally. So in showing you this, I hope this provides some sort of indication of the cost effectiveness and the viability of wind power. There are still many things that we can do, though. A few years ago, the Department of Energy put out a report, their 20% by 2030 report, looking at what it would take in terms of research, innovation, policy to bring wind energy penetration to 20% within the United States. I'm not going to go over all of these, but I will highlight 4 of these topics right over here: passive and active aerodynamic control, grid integration, particularly short-term forecasting, and then how offshore might play a role in the future. So first, when we talk about innovation in wind power, the primary metric that we're talking about is the levelized cost of energy. So the levelized cost of energy is basically all the costs that you incur for the turbine, both the initial capital cost and the operations and maintenance costs over the entire turbine lifetime. So for a wind turbine, that's approximately 20 years. And then we divide that by the total energy production over that full lifetime, that 20-year period. So that's measured in cents per kilowatt hour, and that's our primary metric for success, not only for wind, but just about any generation resource. So it's not the initial capital cost. That might be the case for a small unit, but not for a utility scale unit. It's not the capacity factor or the power coefficient or any sort of physics-based or arbitrary efficiency. So if we wanted to bring the levelized cost of energy down, we could produce more energy. So how can we do that? One way is by making the rotor bigger. So a larger rotor captures more energy. So if I took a blade and I extended it about 5% to 15% longer, we would end up capturing about 10% to 32% more energy. So that's a consequence of the way that power is derived from the wind. It's a function of the area of the rotor. So what that means is that the power is proportional to the blade length squared. Unfortunately, the loads on the blade go up faster than that. They go up proportionally to the blade length cubed. So this, within the industry, is the big conundrum. It's the square cube law. So as you make the rotor larger, you can capture more energy, but then your loads are going up faster. And because your loads are going up with the blade length cubed, your volume has to go up with the blade length cubed, and that means your blade cost has to go up with the blade length cubed. Your cost is outpacing the amount of energy that you can capture. So what can we do to keep those loads down, to keep the blade volume and cost down while capturing more energy? Well, one thing we can do is we can turn to aerodynamic control. Now, I just took this picture the other day as we were landing, and we've been using aerodynamic controls on airplanes for about a century now. Flaps, ailerons, spoilers, all that sort of thing is more than commonplace. So why is this such a big deal for the wind industry? Well, there's 2 things. So first, wind turbines operate in a fantastically difficult regime. It's in the atmospheric boundary layer. There's wind shear, both vertical and horizontal, which means that there's a gradient to the wind as you go up and go across. There's also directional shear, meaning that the wind toward the bottom of the rotor may be coming from a different direction than the wind at the top of the rotor. There's turbulence, so there's a stochastic component to it also, and that can result in gusts that are different down here and over here than up there. And you can imagine that every time a gust goes across the rotor, there's a load that is impinged upon the blades, on the bearings, on the gearbox, in the generator, and that your machine has to be designed to withstand all of that. Second thing are the economics of wind power versus, say, aviation. I was puzzling over this a little bit about how to explain this, because typically when we talk about wind power, as I already said earlier, we talk about the cost of energy, cents per kilowatt hour. And when we talk about aircraft, we talk about revenue per passenger mile. And those numbers really don't compare. So I came up with this instead. So if we take a look at the cost of a wind turbine compared to a Boeing 777, and we look at it the cost per pound. So the weight of a wind turbine and a Boeing 777 end up being about the same, about 320,000 pounds, give or take a few tons. But the cost is dramatically different. So for a 1.5 megawatt turbine, and I'm sorry, the weight that I just gave you was for a GE 1.5, which is the most common wind turbine deployed globally. The cost of that would be on the order of, say, around $1.6 million, $1.7 million. Cost for a Boeing 777, on the other hand, is approximately $260 million. You can go to their website and you can check the price. So you can see 2 orders of magnitude difference in cost. In operating life, about twice that is expected in terms of operating hours for the wind turbine. And if we look at the cost per hour, then again, we have 2 orders of magnitude difference in terms of cost for operation. Now, I'm fully aware that I'm kind of comparing apples and oranges here, but that is kind of my point also, is that we are comparing apples and oranges, and that the economics of these 2 industries are very, very different. But as an old veteran of the industry said not too long ago, wind power is aerospace technology on a sailboat budget. So we can take a look at the methods for aerodynamic control within the lift equation. We'll skip over this very, very quickly. We talked about doing with blade pitch a little bit earlier. We can also do it passively. So this is a sweep twist passive blade, and here the blade is shaped in such a way that as the blade loads and bends backwards, it actually feathers out of the wind too at the same time. And in doing so, the loads decrease as the thrust increases, all by itself. So this is a project that was actually realized and tested in the field. This was done in 2004, took an older turbine, a Zon 48, and put a 52-meter rotor on it. So increased the rotor size and then flew that. I'm going to skip over the results right here and just go straight to the summary. So in doing so, the Star 54, the sweep twist adaptive rotor blade, was able to capture 12% more energy, but at the same time, it retained the same amount, it incurred the same amount of loads as the smaller rotor, Z48, a 48-meter diameter rotor. This turbine is still flying at a hatch speed. If you drive by and see a distinctive rotor, this might be it. So this is kind of heady stuff, passive load control, for not the cost of very much. Of changing the mold, you really do get something for nothing. You get increased energy capture, but you retain the same amount of loads. So in this case, we have worked our way around the square cube law. Another method of aerodynamic control is active load control. So when I say active load control, we saw the photo earlier of the airplane. Flaps, ailerons are ways of actively controlling the aerodynamics on a turbine blade. This is very important because potentially using active control with such devices can replace full blade pitch. So remember I said earlier that blades, that the 48-meter blade that we saw earlier was 9 tons in weight. Nowadays we have turbine diameters going to 120 meters, 160 meters. So eventually we're getting to the point where the pitch drives are having to work very, very hard to drive these very, very hard blades. So if we have a lighter mechanism, such as aerodynamic control, it potentially can replace the pitch drive completely. So a couple mechanisms that we've looked at within our group, microtabs, these are akin to gurney flaps that were developed for race cars in the 1970s, except these are deployable. They're these little guys back over here. And although they're very, very small, only about 1% of the length of the cord, they actually have the same sort of aerodynamic effect as a larger flap. So what we can see over here is that as we deploy the flap either on the upper or lower surface, so these tabs can slide in and out, that we can cause our lift curve to slide up and down. So we've looked at this computationally, we've tested this in the wind tunnel, and then we've actually verified that they are effective. Another technology, microjets. So microjets are very similar to microtabs, but instead of having a small physical device that comes out, we blow air out instead. So it's sort of a fluidic tab instead. Microtabs potentially have the advantage that that you can modulate the effectiveness of them more. Also, you don't have to install a physical device that is difficult to access in the trailing edge of a wind turbine blade. On the flip side, though, the costs of blowing systems have been estimated to be pretty significant. So we've tested this both computationally and in the wind tunnel, and they show a lot of promise. There's a variety of other active aerodynamic control devices that are available too, morphable trailing edges, plasma actuators, and yeah. So I'm going to jump subjects over here and talk a little about grid integration and forecasting. Paul alluded to this a little bit earlier. So about 10 years ago when I first started engaging in wind, I was surprised to find out that most of the technological questions weren't about turbine technology, but instead was about how the wind power, that the wind electricity was going to integrate in with the larger grid electricity supply. And you can sort of see the problem right over here. This is what the load is doing, and then this is what the wind's doing, which has a largely variable component. So how do those two interface to provide reliable electricity to us? So over the past 10 years, there's been a large number of grid integration studies. We've come to understand very well wind generation patterns, the impact of wind on contingency reserves, system reliability, transmission requirements, what sort of penetration levels the grid can bear of wind. One area of research that's ongoing is looking at forecasting of short-term ramps. So when I say short-term ramps, this is the wind power output of a single plant. And you can see within this short 10-minute period over here, we have a rather large drop. Similarly, you can also have large swing increases too as the wind picks up and then increases beyond the cut-in speed, and suddenly wind production jumps up. So this graph over here shows the ramp events over a 1.5-year period, and the background over here indicates the magnitude of the wind ramps that are encountered, and the larger events are called out with these circles. And we can see that there are relatively very few of these. So for a plant that's 24 megawatts in size, the largest ones that are incurred are plus or minus 17 megawatts. So the questions that we're looking at today are, well, what is a large ramp from a grid operations perspective? And one of the projects that we're engaged in is the WindSense project. That's down in the Tehachapi area. The Tehachapi area is the largest wind resource area in California. It includes the Alta Wind Energy Center, which is a gigawatt size and project currently. Tehachapi is predicted to ultimately have 4,500 megawatts of wind. So we're looking at a capability to provide a 0 to 6 hour forecast for these short-term ramps into Tehachapi, and we're going to do that by deploying upwind sensors, LiDAR, radiometers, et cetera. And this is a project that we're doing in collaboration with the CEC and with CalISO. So that's the Tehachapi area right over here. I'd like to call out for my last topic that I'll talk about this wind resource out here, this large offshore wind resource. So offshore is considered to be the large untapped resource that's available. And currently there's it's estimated that there are more than 4,000 gigawatts of offshore wind available. It's a large aerodynamically clean resource. That is, it's low turbulence. It's conveniently near load centers. Unfortunately, about 74% of that is in deep water. There's very little experience with deep water offshore plants, and there's no offshore plants in the United States currently. So if we look ahead into the opportunities and the challenges ahead, we'll start with the negatives first. So if we look at offshore turbines, we can expect them to have higher capital and O&M costs. For deep water, we'll have to deal with moorings, floating platforms for deep water, much more complex structural dynamics. Can have to contend with underwater transmission. That will be offset by the fact that they can be closer to load sources. New regulatory processes for permitting. The offshore projects that have been proposed so far are encountering those. And then new environmental considerations also. On the plus side, again, it's a very, very large resource, potentially very close to load centers, a low turbulence resource, and potentially less visual and acoustic impact also. So the benefit of that is potentially we can shift over to alternative configurations for turbines. I'm working with a company currently where we're looking at a 2-blade downwind turbine, something that hasn't been considered for terrestrial use in a very long time, but could be very appropriate for offshore use. So final thoughts is that wind power is a mature and viable technology. There's 240 gigawatts of it currently installed, but there's still a lot of things that we can do to make the technology better. Better turbines through advanced rotors and blades, better grid integration, including the short-term forecasting that I talked about briefly, and then also looking at new resources such as offshore. Thanks.